Hello, everyone. Welcome back. So last time we talked about the linear programming basics, and we also discussed a little bit about the few assumptions of the linear programming. And also we've learned how the practical solutions can be formulated as linear programs with couple of the simple examples, right? So today we are going to talk about graphical method for linear programming models. Especially this technique is useful for the linear program with only two decision variables. So what is that? Okay, here's my slide. Okay. So first of all, I'm going to discuss the couple of the professional terminologies related to LPs. Okay. So first, the solution. So in our everyday life, the term solution means the final answer to a certain problem, right? But in LP, in linear programming model, any specification of values for the decision variables, X or Y, is called a solution, okay? And a feasible solution is a solution for that all of the constraints are satisfied, including the sign restrictions. Okay. In other words, an infeasible solution is a solution that at least one of the constraints, even the sign restriction, is violated. Okay, so definitely we are not interested in the infeasible solution. Okay, and the feasible reason is the collection of all the feasible solutions. So the feasible reason for any LP is a set of all the points satisfying all of the LP's constraints and the sign restrictions as well. Okay. Next is the optimal solution. An optimal solution is a feasible solution that has the most favorable values of the objective function. So here, the most favorable value could be the largest value if the objective function is to be maximized. Of course, it's going to be the smallest value if the objective function is to be minimized, right? And if there is no other feasible solution with objective function value better than that, okay. So that's the optimal solution. And the optimal value of a problem is the objective function value of an optimal solution to the problem, okay? So we're gonna keep coming back on these different terminologies: solution, feasible solution, infeasible solution, and optimal solution, and optimal objective function value, okay? Okay, so let's consider a very simple LP example. So in this case, x1 equals 2/3 and x2 equals 7/15 is a feasible solution. Actually, I can get that value from the second constraint here, x1. So if you divide by 3 on both sides of the second constraint, then you would get the x1 equals 2/3, right? And then if you plug in then the first constraint will give you x2 equals 715, right? So actually, this is the only solution to the problem, right? So it is also the optimal solution to the problems as well, okay? Of course, the optimal objective function value would be 2.73, okay, from the objective function value, with x1 equals 2/3, x2 equals 7/15, right? So this case is very simple, straightforward. Now, let's reconsider the window glass example that we discussed during the last time. So in this LP model, x1 equals 0, x2 equals 0, for example, is a feasible solution with the corresponding objective function value of g equals 0, right? Then is that going to be the optimal solution? No. Because we want to maximize x1, 3x1 plus 5x2, right? Although x1 equals 0, x2 equals 0 can satisfy all of these constraints, including the sign restriction, we know that this cannot be the optimal solution, okay? Because the objective function value can be improved a lot by increasing the value of x1 and the value of x2. Is that correct? So for example, with x1 equals 0 and x2 equals 4, we obtain another feasible solution, which has larger objective function value, which is 20, right? So obviously this is better than the first case, right? But can you say this is the optimal solution to this window glass problem? You could answer this question very easily through the graphical method, graphical procedures. Okay. So I just let you know that any LP, any linear programming model with only 2 decision variables can be solved graphically. Okay. And this graphical procedure involves constructing a 2-dimensional graph with x1 and x2, in this case, as the 2 different axes, right? Horizontal axis and vertical axis. Right? And the first step is to identify the values of x1 and x2 that are permitted by the restrictions. And this is done by drawing each line that borders the range of the permissible values for one restriction. So first, the non-negativity restrictions. x1 has to be greater than or equal to 0, and x2 has to be greater than or equal to 0. This non-negativity restriction requires x1 and x2 to lie on the positive side of the axis, right? Which is this area, which is the first quadrant, right? Next, the restriction x1 is less than or equal to 4 means that x1, x2 cannot lie to the right of this line, x1 equals 4, right? So far, our feasible reason would be this area, okay? So likewise, the restriction 2x2 is less than or equal to 12 implies that the line 2x2 is less than equals 12 should be added to the boundary of the permissible region, right? So far, our feasible region would be this rectangle, right? And the final restriction, the third constraint, 3x2, 3x1 plus 2x2 is less than equals 18 is also added to complete the boundaries, right? Which is this. And the feasible region should be this side. How do you know that? For example, if you plug in the origin value, 0, 0, into this constraint, so 3 times 0 plus 2 times 0, which is 0, is less than equals 18, right? So 0, 0 satisfy this constraint, meaning that this point, origin point 0, 0 should be one of the feasible points concerning this inequality constraint, right? So that's why the feasible region should be this side, so that the feasible region does include the origin point, okay? So we know that this origin is one of the feasible point. So the resulting region of permissible values of x1 and x2 are called the feasible region, okay? Okay, now I want you to recall your memory. So what is the extreme point in this feasible region? How many extreme points do we have? The extreme points of this feasible region are simply these 5 different points, right? 1, 2, 3, 4, 5, right? You remember last time I mentioned in this area, linear programming, extreme points are the corner points, okay? Because if the feasible region is a polygon like this, the extreme points of the feasible region will be the vertices or the corners of the polygon all the time in the linear programming area, okay? Okay, so having identified the feasible region for our case window glass example problem, now we can search for the optimal solution. So that will be the point in the feasible region with the largest value of 3x1 plus 5x2. Is that right? That's our objective function. So to find the optimal solution, we need to graph a line on which all of the points have the same objective function value, okay? So in a maximization problem, just like ours, such a line is called an ISO value, ISO profit line, okay? So it's gonna be ISO profit line. Of course, in a minimization problem, that's going to be the ISO cost line, okay, in the minimization. But in general, such a line is called an ISO value line, okay? That's for the specifically for maximization problem, and this is for the minimization problem. And in general, it is called the ISO value line, okay? So let's use ISO value line, okay, from now on in this class. Okay, then the question is, how can you draw an ISO value line? to draw an iso value line, what you need to do is to choose any point in the feasible region. Okay, it could be the one from the inside the feasible region, or the boundaries of the feasible region, or in the corner point, extreme points of the feasible region. It really doesn't matter. Just choose any point in the feasible region and then calculate its objective function value. So let's do that. Okay, so let's choose 0.04. Just arbitrarily, we choose this point, okay? And then for 0.04, okay. So for 0.04, so if you plug in 0 and 4 to the objective function, right? Then 3 times 0 plus 5 times 4 becomes 20. That's why for 0.4, the objective function value will be 20, okay? So this means that the point 0.4 lies on the iso value line, 3x1 plus 5x2 equals 20, okay? And rewriting this as x2 5x2 equals, so we're going to move this to the right hand side, negative 3x1 plus 20, right? And then divide both sides, 5, right? It's going to be negative 3/5 x1 plus 4. So is that right? So this is going to be our iso value line at 0.04. And this line has a slope of negative 3/5 and x2 intercept of 4. Is that right? So, okay, it just looks like this. And all iso value lines have the same slope because all iso value lines are of the form of 3x1 plus 5x2 equals constant values, okay? Just like us, right? So this means that, you see this clearly? Okay, so this means that once we have drawn one iso value line, we can find all other iso value lines by moving parallel to the iso value line we have just drawn. Is that correct? So in this problem, the objective function z will decrease if we move in a direction for that both x1 and x2 decrease, right? See here, if x1 value decrease and x2 value decrease, then our objective function value will decrease. So we construct additional iso value line by moving parallel to 3x1 plus 5x2 equals 10, right? In a, what is that? The southwest direction. in this case, right? So of course, in this case, the x1 value, x1 value has been decreased, right? From here to here. Likewise, x2 value has been decreased from here to here, okay? By moving this iso value line to this direction. Is that right? Okay. Likewise, the objective function value z will increase if we move in a direction. For that, both x1 and x2 increase. So we construct additional iso value line, right? By moving parallel to this 3x1 plus 5x2 equals 36 in a northeast direction. So in this direction, right? So of course, starting from here, x2 value has been increased to this much, right? Likewise, x1 value also been increased by this much, okay? Now we know that the optimal value of 36 for this problem would be found with the iso value line intersecting or touching the feasible region, okay? Okay, so once the optimal solution to the LP problem has been found, it is very useful to classify each constraint as being a binding constraint or a non-binding constraint, okay? So graphically, it's very easy to see which constraint a binding constraint and which constraints are non-binding constraint. So let's take a look, consider our example, window glass example problem. So for the optimal point, which is this point, right? Optimal point, this constraint is non-binding. And these two constraints are binding constraints, right? So for the non-binding constraint, how do you know that? If there is a positive gap between the line and the optimal point, right? So there is a positive gap between this line and our objective, our optimal point here, right? Then this constraint is going to be non-binding constraint, okay? So similarly, if there is no gap between the line and the optimal point, then the corresponding constraints is binding constraint. That's why at the optimal point, we have two binding constraints, okay? So identifying which constraints are binding constraints are very important because we know that optimal point occurs at the intersection of these two binding constraints. These two lines actually in this case, okay? So which means that if you solve these two equations that are representing each of these two lines, right? Then you should be able to get the optimal solution. So in our case, it's going to be x1 equals 2, x2 equals 2, okay? Of course, if you use this x1 and x2 value in our objective function, then we will obtain the corresponding optimal objective function value of 36, okay? So we'd say that the maximum profit for the window glass company should be $36 or $36,000, whatever, okay, the unit. Okay, then let's consider another very simple example. Okay, now let me give you like a couple minutes. So why don't you pause this lecture video and then try to do it by yourself and then come back and then compare yours with mine, okay? Okay, so we want to find the optimal solution for this simple example using the graphical method we just talked about. So as you've already noticed, this shaded area is the feasible reason, okay? So how many extreme points we have in the feasible region? Again, we have 1, 2, 3, 4, 5. 5 extreme points, 5 corner points, right? So if there is an optimal solution, then the optimal solution should be one of these extreme points. Is that right? Okay, so to find the optimal solution, we need to graph an ISO value line, right? And to draw the ISO value line, what you need to do is just choose any one point in the feasible region and then calculate its objective function value. So okay, so let's choose point 0.01. Okay, let me. Okay, here's my cursor. Sorry. Okay, sorry, I just want to remove what I marked earlier. Okay, so let's choose 0.01 in this case. So we have 0.01. So arbitrarily we selected 0.1. Okay. So which is like right here. Okay. And for 0.1, so for 0.1, the corresponding objective function value is going to be -2 times 0 minus 1. So how much is that? So is that going to be -3? So this means that the 0.01 lies on the ISO value line, -2x minus y equals I'm sorry, it's going to be -1, right? Because this becomes 0. So this is going to be 1. So this is the ISO value line at 0.01. -2x minus y equals -1. Okay, that's our ISO value line. Okay, so like this here. So by moving parallel to the ISO value line we have just drawn, in a northeast direction, we could improve the value of z, which is -2. Okay. If you move further to the northeast direction, then we could improve the value of z, which is -4. If you move further in the northeast direction, then the objective function value becomes -5. Okay, and this is the last isovalue line intersecting the feasible region, right? So that means after this point, if you move further to the northeast direction, then the isovalue line will no longer intersect the feasible region, right? So we shouldn't do that, okay? So we have to stay within the feasible region to get the optimal solution. So keep in mind that, right? So we may conclude that the optimal solution has been found with x equals 2 and y equals 1, okay? And what is the objective function value? -2 times 2 minus 1. How much is that? -5. That's why we have -5 here. Okay. Okay, then let me ask you. So at this optimal point, which constraint is binding and which constraint is non-binding? So this optimal point, we have two binding constraints, right? There's two binding constraints. And this constraint is non-binding constraint. Is that right? Okay. So these slides, next slide, shows the required steps of the graphical method for solving the linear programming model. So the very first step is to identify the feasible region. Okay. Right after that, you need to plot an isovalue line corresponding to a feasible solution, and then move the isovalue line in an improving direction. And you need to identify the last isovalue line that intersecting the feasible region, okay? And any point on the intersection of the last isovalue line and the feasible regions are optimal solutions, okay? Okay, so let's take another simple examples for the graphical method. So so in this case, the feasible region would be another polygon shaped like this, and that has 5 different extreme points, just like our previous case, right? But in this case, the ISO value line looks a little bit different, right? So in this case, we need to move this ISO value line in the direction that X1 value will be decreased and X2 value will be increased, right? Because it has negative sign here. And we want to minimize this value, right? So you have to move ISO value line in this direction. And then the last ISO value line, the touching the visible region should be this one. That's why we have optimal point occurs right here. Okay. Okay, what about this case? Again, I do highly recommend you to pause the video recording and then try to do it by yourself and then come back and compare the solution with me, okay? So in this case, ISO value line, one of the ISO value line would be just looks like this. And we need to move ISO value line in this direction, okay? And okay, just one small thing I want to mention is right now, our objective function is minimizing negative 2x1 minus x2, right? So this is the identical to minimizing. I take out negative sign, then we have 2x1 plus x2, right? So here, this would be exactly same as maximizing 2x1 plus x2. Is that right? Because minimizing the negative function would be exactly the same as maximizing the positive function. Okay. So to improve the objective function value, you have to move ISO value line in this direction. In a way, your x1 value will be increased as well as x2 values. Is that right? Because you want to maximize this. So the very last ISO value line would be like this, that touch the visible region, okay? So that we can indicate optimal point right here. Okay, so this is another example. Here, in this case, one of the constraint has the same slope as the ISO value line, right? Because here, the first constraint, left-hand side, is identical to our objective function, right? So in this case, the feasible region consists of just the dark line segment, okay, between the point 2,4 and 4,2, okay? Because the points on these line segments are the only ones that simultaneously satisfy all of the constraints, okay? So all of these points must be the optimal point, okay, on this line segment between these 2 points, okay? So, which means we have multiple optimal solutions. Actually, we have infinite number of optimal solutions in this case. So in this case, all of the points in this dark line segments for the optimal. Okay. Okay. So far we've discussed the graphical approach for solving the linear programming model, right? And the graphical method, as you can see here, works very well for any LPs with having only two decision variables. Okay, it can be used for three decision variable case. However, it will be very complicated because you need to deal with three-dimensional graphs, right? And of course, it's impossible for you to consider for the case with four or more decision variables, linear programming model, right? So in that case, other solution approaches are necessary, right? So but at least I would say the graphical method is very good to illustrate the concepts and also the helps in conceptual understandings. Okay, so what's next? Oh, okay. So now we're going to talk about three different types of LPs that do not have the unique optimal solutions. Okay. So like it says, whenever a linear program has an optimal solution and it has a corner, there is always an optimal solution on one of the corners of the feasible reason. However, it doesn't mean that the linear program always has an optimal solution. Okay. And also, it does not say that all of the optimal solutions have to be on the corners, right? I just show you that special case, right? So let's discuss what are the possibilities that a linear program does not have an optimal solution at a corner point. So first, the infeasibility case, okay? So in this case, there is no real value that is simultaneously less than equal to -1 and greater than equal to 0. Is that right? So in this case, the feasible reason is going to be empty. The feasible reason contains no points, right? Resulting in an infeasible LP, okay? Because the optimal solution to any LP is the best point in those feasible reasons. So an infeasible LP has no optimal solution, okay? So, okay, so this shows a general case of the infeasible LPs because there is no feasible reason that simultaneously satisfy all of the constraints, including the sign restriction. So the feasible reason is going to be empty. So these result in an infeasible LPs, okay? So what is the other possibility that a linear program does not have an optimal solution at a corner point? The next case is what is called unboundedness, okay? So in this case, the linear program is feasible to solve, but the optimal value is not finite, okay? For example, in this LP case, okay, so I already draw the feasible reason, everything here. So this is very special LP, right? So which is, of course, the unbounded LP. So as you can see here, when graphically solving an LP, we can spot an unbounded LP very easily. So in our case is the maximization problem, right? So in this case, this is the isovalue line, right? This is the isovalue line. And we need to move isovalue line to the northeast direction to improve its objective function value, right? But what's the problem? When you move parallel to our original isovalue line in this direction of increasing the objective function value of z, what happened? We never entirely leave the feasible reason, right? We never leave the feasible reason. Okay, that's why this case is called unbounded. Yes. Okay. So we call this the given LP is the unbounded LP. Okay. This shows a general case of unbounded LPs. Of course, likewise, for the minimization problem is unbounded if we never leave the feasible reason, okay? When you move the isovalue line in a direction of decreasing the objective function value in that case. Okay, so what is the other possibility that a linear program does not have an optimal solution at a corner point? So we just talked about that, right? One of the last example problem that we discussed in this case. So in this case, one of the constraints has the same slope, right, as the isovalue line. So in our case, first constraint is the same slope as the isovalue line. So the feasible reason consists of just this dark line segment, okay, between these 2 points. So all the points in this dark line segments are the optimal, okay? So some of the LPs have some infinite number of optimal solutions. So this is the case, okay? And this shows a general case of multiple optima. Okay, so in summary, we see that every LP must fall into one of these 4 different cases. Okay, keep in mind that. So the first case, the LP has a unique optimal solution. And also LP could have alternative or multiple or infinite number of optimal solutions. Okay, so that's going to be the second case. The third case, the given LP could be infeasible to solve, okay, because the feasible reason contains no points, okay. And the last case would be unbounded LPs. So there are the points in the feasible reason with arbitrarily large objective function value in the maximization problem, or arbitrarily very small objective function values for the case of minimization problems. Okay. Okay. So let's, since we have some times left, let's consider one exercise problem. What is that? I think this one. Okay. So let's consider this exercise problem. Let me zoom in a little bit. Okay. Okay, so this is the given LP, maximizing 3x1 plus 2x2, subject to 3 constraint sets, also having the non-negativity restrictions. So we want to identify the optimal solution using the graphical method in this case. Okay. So again, let me give you like 5 to 10 minutes. So why don't you pause the video recording and then try to do it by yourself and then come back your solution with mine. Okay. So the very first step is to identify the feasible reason. Okay. So let me, okay, let me try to write here. So we can rewrite each constraint. So if I move x2 to the right-hand side, then it's going to be x2 greater than equals x1 minus 4. Or you can multiply -1 on both sides and then move x1 term to the right-hand side. So you're going to have this, right? And for the second constraint, it's going to be okay. So what I'm going to do is I'm going to move negative x1 to the right-hand side and then divide both sides by 2, okay? And it's going to be x2 less than equals 1/2 x1 plus 1. So this is the constraint number 1, constraint number 2 prime, okay? And about third constraint. So it's very similarly, I'm going to move x1 to the other side and then divide both sides by 2. So that's going to be x2 less than equals negative 1/2 x1 plus 3. Okay. So let's call it constraint number 3 prime. So based on this, let's draw a feasible reason. It's very neat. Okay, I can move the screen. Okay, that's cool. Okay. It's way better than the PowerPoint slides then. Okay, so let's move a little bit. Okay. Then let me draw 2 axes. Good. And let's say this is going to be x1 axis and then x2 axis. Okay. And the first constraint has slope of 1 and x2 intercept of 4, of -4. So let me do this. 1, 2, 3, 4, -4. And then 1, 2, 3, 4. So I'm going to draw line, something like this. Okay. So this is going to be our constraint number 1 prime, or 1 is fine. Okay. And what about the second constraint? It has slope of 1/2 and x2 intercept of 1. So it has something like this: 1, 2, 3, 4, 5. So starting from here, the slope is 1/2. So we're going to cross this, right? So something like this, okay? Wait a second. How can I delete it? Okay, like this. Okay. Cool. Oh, very cool. So this is the one. Constraint number 1 is right here. And I'm going to delete this. This is constraint number 2. And the third constraint has slope of -1/2 and x2 intercept of 3. So we start from here. One, two, three, 4, 5, 6. Something like that. So if you're gonna cross this, right? So this is gonna be constraint number 3. And our feasible reason should be where? I'm gonna change the color. So our feasible reason should be this area. How do we know? So for each constraint, the origin 0, 0 does satisfy or not. So here 0 is greater than equal to 0 minus 4, which is -4, which is true, right? So concerning the first constraint here, the feasible region should be this side, right? In a way, the origin point should be one of the feasible point, okay? Likewise, for constraint number 2, 0 is less than equal to 0 plus 1, which is 1. So this is true as well, which means the feasible region should be this side. In a way, this 0 origin should be one of the visible point. How about the third constraint? 0 is less than or equal to 0 plus 3, which is 3. So it's correct, right? So visible region should be this side. As a result, our visible region should be this polygon, okay? So in this polygon, we have 1, 2, 3, 4, 5 different corner points, extreme points, right? So if this given LP has an optimal solution, then one of these extreme points should be the optimal point, okay? Okay, now we identify the feasible region. The next step is to plot an isovalue line corresponding to these feasible solutions, right? Let's change the color. Oh, okay. So let's choose any point in the feasible region. Like I said, it could be one from the inside the feasible region, or the boundaries, or the corner point. It really doesn't matter. Okay. So how about let's choose point 20. Okay. And then for this point 20, we need to compute the corresponding objective function value. So our objective function is 3 times x1 plus 2 times x2, right? So that's going to be 6, which means that this point 20 lies on the isovalue line, which is 3x1 plus 2x2 equals 6, okay? So this is going to be our isovalue line. And if I rewrite this, it's going to be x2 equals, how much is that? Negative 3/2 x1 plus 3, right? So I just move 3x1 to the other side and then divided by 2 on both sides, right? So this is going to be that. So our isovalue line has a slope of negative 3/2 and x2 intercept of 3. Okay. So it's going to be like this. This is our isovalue line. Now we need to move this isovalue line in a direction, in an improving direction, right? So in this case, both x1 and x2 values increasing, okay, because we want to maximize 3x1 plus 2x2. So obviously we need to move our isovalue line in this direction. So we're gonna draw many of them, and then eventually we're gonna get this one. This is gonna be the last isovalue line, which touching the feasible region, right? So this is gonna be our optimal point, okay? now, because we identify the optimal point, right? So we need to identify binding constraint according to this optimal point, okay? So we have, let me change the color. So we have two binding constraints, which is constraint number 1 and then constraint number 3, right? So we have two binding constraints, this optimal point. So what you need to do is just solve these two equations. So here, first equation would be x1 minus x2 equals 4. And the third equation, right, would be this, x1 plus 2x2 equals 6. So if you solve this, then you together get the optimal solution. So from here, x2, x1 equals x2 plus 4. So instead of x1, I can use this, right? So from here, x1 is going to be, how much is that? No, x2 first, right? How much is that? x2 is going to be, is that 2/3, right? Okay. And then how about x1? x1 is going to be, it's going to be 14/3. Okay. So the corresponding optimal objective function values going to be 3x1 2/3 plus 2 times 14/3. So how much is that? So going to be so 46. Yeah, 46/3. So that's our optimal objective function value. So I'm going to put the asterisk indicating the optimal objective function value. Likewise, I'm going to put the asterisk here. So this is the optimal solution, okay? Okay, I believe this is all for today. So next time, I'm going to give you more example so we can practice the graphical method for solving the linear programming problem, okay? Okay. Thank you everyone. Okay, so I will see you next time. Thank you. Bye-bye.